covers a large portion in the competitive exams, and students generally face a lot of difficulty in understanding the concepts of organic chemistry. Here in this course, I've tried to cover every basic detail of this organic chemistry, and I've tried to simplify the discussions as far as it was possible. So let's start with some basic principles that are involved in organic chemistry. Now, first of all, let us know that what is organic chemistry and what is the difference between organic chemistry and inorganic chemistry. So talking of organic chemistry, it is that branch of chemistry that deals with the study of carbon and its compounds. Along with carbon, the compounds may also contain other elements such as hydrogen, oxygen, nitrogen, sulfur, etc. So whatever compound we will be talking about, it will definitely contain the element carbon in it. So that is why a separate branch has been made for the study of carbon. Now, why for the study of carbon only a separate branch has been made is because carbon forms a part of majority of living matter present on the earth, and also the number of compounds of carbon is so huge that it becomes necessary to create a separate branch for this element. On the other hand, we have inorganic chemistry, which is that branch of chemistry that deals with the study of all the elements other than carbon and its compounds. So whatever other elements are left, they all are studied in the inorganic chemistry. Now the next question that comes across our mind is that why does only carbon form such a huge number of compounds? So this is because carbon shows the property of catenation or self-linking. So many carbon atoms can join together with one another and form long chains of carbon compounds, and also they can form rings of carbon, and the compounds may also be present in the branched form. The next property is of tetravalency. Carbon doesn't form 1, 2 or 3 bonds, but it forms 4 bonds in total, and that means that it can be further connected to 4 other elements that may be carbon or any other element as well, such as hydrogen, oxygen, nitrogen, sulfur, etc. So the next topic that we'll be going through is the hybrid. So about hybridization, I've already discussed this in the chapter Chemical Bonding and Molecular Structure. So let's just have a quick overview of what is hybridization. So hybridization is the intermixing and redistribution of pure atomic orbitals to prepare new orbitals. So the new orbitals that are prepared would have equivalent shape, size and energy. So here we have the example of a methane molecule. A methane molecule would be formed by the 4 orbitals of carbon, s and 3 p orbitals. S orbital have a different energy, whereas the p orbitals are different in energy, shape and size from that of the s orbital. A compound would only be formed in this case if all these orbitals combine together and form a new set of orbitals known as the hybridized orbitals, which have equivalent shape, size and energy. So the new orbitals here formed would be known as the sp3 hybridized orbitals, because they are formed from 1s and 3p orbitals, and this is the orbital structure that we can show here. When talking of the hybridization of ethene, ethene has a double bond between carbon atoms. Now since it has a double bond, so one of these bonds would be a sigma bond and the other bond would be a pi bond. So one one of the p electrons would be involved in the formation of a pi bond by the overlapping of these p orbitals, whereas the other three orbitals would combine together and form hybridized orbital known as the sp2 hybridized orbital. Now this is how actually we calculate the hybridization of the carbon atom present. So if the carbon atom has 3 sigma bonds in it, so 1, 2 and 3, then the hybridization would be sp2 hybridization. In the earlier it had 4 sigma bonds, 1, 2 and 3 and 4 sigma bonds. So the hybridization in this case was sp3 hybridization. Now in case of ethyne, it has only 2 sigma bonds, one here and one in the triple bond, because the other 2 bonds will be the pi bonds. So in this case the hybridization would involve only the mixing of 2 orbitals s and p orbital, because the other 2 p orbitals would be involved in the formation of pi bond by the sideways overlapping of the p orbitals. So we say that both these carbons in this case, because they have only 2 sigma bonds, would possess a sp hybridized orbital. Now I've just given you here the overview of the hybridization. In case you want to understand it very nicely and in full detail, please go through my lecture on chemical bonding and molecular structure. Okay, now so let us see that how do we represent the organic molecules in 3-dimensional form using a structural diagram. So in the subsequent lectures, many a times I'll be using these type of bonds. You must have seen this line bonds, but in the subsequent lectures we'll also be using solid wedge bonds and the dash wedge bonds to know that how a molecule actually looks like in 3-dimensional space. So these single line bonds are the simple bonds, and these mean that the molecule or the atoms are just present in the plane of the paper. Now if I've drawn this dashed wedge bond, this means that the atom here is away from the observer. That is, it is not present in the plane of the paper, but it is present below the plane of the paper. The next one is the solid wedge bond. It means that the atom here is present above the plane of the paper, that is towards the observer. All these bonds are just simple covalent bonds, and each of these are made from 2 electrons each. The only difference is that we are just showing that in which direction these atoms are present. Now next we have the effect of hybridization on the bond length and bond strength. So we'll see here that which type of hybridization forms a stronger bond, sp3 hybridization, sp2 or sp hybridized orbitals. So we know that p orbital is much bigger in size than an s orbital of the same subshell. So p orbitals have a larger size, whereas the s orbitals are smaller in size. Now let's calculate the percentage of p orbitals present in each of the hybridized orbitals. So if sp3 hybridized orbitals are present, it will contain an s orbital and 3 p orbitals. Therefore, it will have 25% s character, whereas the whatever is left, that is 75%, that will be of p character. Similarly, here there are 3 orbitals, so 33.3% it would show the s character, and 66.7% would be a p character that would be shown by this orbital. Similarly, in the case of sp hybridized orbital, it would be 50% s character and 50% p character. So the size of the orbitals would also decrease in the same order. p orbitals are bigger in size and sp3 hybridized orbital have a greater p character. Therefore, sp3 hybridized orbital would be the largest in size. Further, sp2 hybridized have 66.7% p character. Next, which is less than the sp3 hybridized, so it will come next to this. That is, it will be a bit smaller in size. And lastly, the least p character is of the sp hybridized orbital, so it will be the smallest in size out of all these three orbitals. Now, according to the size of these orbitals, we'll see that how does it influence the length of the bond. Now, greater the size of the orbital, longer will be the bond formed. So, sp3 hybridized orbital is the greatest in size. Therefore, a bond formed between two carbon atoms which are sp3 hybridized would be the longest. And sp hybridized is the smallest orbital out of these three. Therefore, a shorter bond will be formed between two sp hybridized carbon atoms. And the sp2 hybridized carbon-carbon bond comes intermediate between both of these. Now, based on the bond length, we'll see how does the bond length affects the bond strength. That is, how stronger is the bond. So, shorter the bond, greater will be its strength, because both the atoms would be tightly bonded to each other. So, this was the order of the bond length in which sp3 hybridized carbon atoms had the greatest bond length and sp hybridized carbon atoms had the shortest bond length. So, the shortest bond would have the greatest bond strength, and therefore the sp hybridized carbon-carbon bond would be the strongest bond, whereas the sp3 hybridized carbon-carbon bond would be the weakest bond out of all these. So, based on all these, we have some sample problems. So, the first one is, how many sigma and pi bonds are present in each of the following molecules? So, whatever compound is given to you, first of all, you're supposed to write its structure. After writing the structure, count the number of bonds. Single bonds, all the single bonds would be sigma bond. So, 1, 2, 3, 4, 5 sigma bonds. Plus, we also have a triple bond here. Out of all these three, only one would be sigma and the other two would be pi bonds. Therefore, in total, we have 6 sigma bonds and 2 pi bonds. In the next part, we have all these as single bonds. So, all of them would be sigma bonds. So, when you count all these, it will come out to be 13 sigma bonds. The next one is, what is the type of hybridization of each carbon in the following compounds? Again, you will first draw the structure and then we'll count the number of sigma bonds. 1, 2, 3, 4. 4 sigma bonds, therefore sp3 hybridized. In this case also 4 sigma bonds, it will be sp3 hybridized. This one also contains 4 sigma bonds and it will be sp3 hybridized. Whereas this carbon contains 3 sigma bonds and 1 pi bond. 3 sigma bonds mean sp2 hybridized orbital. Similarly, you can calculate for this one. In this carbon, there will be 2 sigma bonds, 2 pi bonds. Therefore, it will have a hybridization of sp. So, this was all for this lecture. In case you have any queries, please write it in the comment section. Please like the video, share and subscribe it.